Welcome to This Explainer. I'm going to be your personal troubleshooter today. We're going to tackle one of the most frustrating, high-stakes realities of training massive AI models. Look, you've been there, right? You've spent hours, maybe even days, designing this absolutely perfect architecture. You prepped your dataset, you meticulously set up your environment, you finally hit run, and you sit back, watching that console with eager anticipation.
And then, boom, disaster. Step 1, loss is NaN, not a number. Your model just died on the operating table, completely destroying your entire computation lane. It is literally the ultimate pain point for anyone working with transformers or deep reinforcement learning agents. You just stare at your screen, wondering where on earth your logic went wrong. Did you completely mess up the calculus? Is your math just fundamentally flawed?
Okay, let's take a breath, because the answer is almost always no. Honestly, your pure math is probably perfect. The real issue is something we call numerical stability. This is the engineering discipline of writing mathematical equations in a way that prevents finite computer hardware from crashing. You see, pure mathematics is continuous. It's infinite. But your GPU, it's discrete. It's strictly finite. So when your beautiful, infinite pure math crashes headfirst into the very real physical memory limits of silicon, you get NaN, you get infinity, or you get these silent, model-killing zeros.
To really wrap our heads around this, let's do a little skit. Imagine you're an accountant, but you're working with this incredibly cheap, tiny little calculator that can only hold exactly 3 digits. No more. Well, this is exactly what your GPU is dealing with, just on a slightly larger scale. Now imagine you need to calculate the probability of 10 independent events, and each one has a 10% chance. Mathematically, that is 0.1 times 0.1 times 0.1 10 times over. Pure math says the answer is 10 to the power of -10. Simple, right? But our little 3-digit calculator? It does 0.1 times 0.1, getting 0.01, then 0.01 times 0.1, getting 0.001, and then it tries to multiply by 0.1 again. The calculator just runs out of physical space. It forcefully rounds to exactly 0.0, and it stays 0.0 forever. This perfectly illustrates the underflow problem. Your gradient just died, and all that multiplicative information is permanently destroyed.
But wait, our trusty little 3-digit calculator is not done failing us just yet. Let's try the exact opposite problem. Let's ask it to calculate e to the power of 100. Now, mathematically, this is just a massive, exact, real number. But when you punch that into our limited calculator, the physical register simply cannot hold a number that massive. It literally has a meltdown. It throws an error, prints inf for infinity, and gives up. Your GPU cannot approximate it, it just physically surrenders. And that right there is the overflow problem. Let's picture this on a floating point number line. Imagine a continuous line, but here's the catch. As you move further out to the right, the numbers aren't evenly spaced anymore. The gaps between representable numbers actually start expanding exponentially. Eventually, you hit what I like to call the cliffs of overflow. Right at the edge of this hardware limit, there's a massive gap, and then just a vertical wall labeled plus infinity. If your mathematical result, say a huge dot product in an attention layer, creeps up and falls into this massive gap near the edge, the GPU violently snaps it to infinity. And any subsequent math you try to do after that, like infinity minus infinity, it instantly yields NaN. Your model is dead. Now let's contrast those massive cliffs with the very center of the number line, right around 0. Welcome to the black hole of underflow. Between 0 and say 0.000001, pure math says there are infinite real numbers, but your computer, it only has a finite number of bits. So below a certain tiny threshold, the computer simply throws its hands up and snaps the value to exactly 0.0. If a delicate, tiny gradient falls into this black hole, multiplying it by 0 keeps it dead forever. Absolutely zero learning happens. So how do the pros actually fix this? This is especially critical when dealing with something like the softmax function, which demands calculating exponentials. Imagine we need to sum e to the 1000, 1001, and 1002. These values extend way, way beyond standard hardware limits. They are instantly crashing into that infinity zone we just talked about. If we try to sum these natively, we get inf, and then taking the log of inf gives us our dreaded NaN. We desperately need a mechanical rescue. Enter the Log-Sum-Exp trick. This is literally the ultimate pro secret in deep learning, and here's exactly how it works. Step 1. We look at our set and find the absolute maximum value. Here, it's 1002. Step 2 is where the absolute magic happens. we mathematically shift the entire x-axis to the left by exactly 1002 units. We do this by factoring out e to the 1002. And step 3, because we shifted that axis, our previously massive model-breaking exponential bars dramatically shrink down to a perfectly manageable size. Just look at how beautifully satisfying this result is. By shifting the axis by 1002, those massive bars of e to the 1000, 1001, and 1002 have instantly shrunk down into e to the -2, e to the -1, and e to the 0, which evaluates to roughly 0.13, 0.36, and exactly 1.0. The astronomically huge numbers have been successfully shrunk into safe, tiny fractions that the hardware can easily sum without ever getting close to infinity. Once the sum is done, we mathematically shift the axis back up by adding 1002. We get the exact same mathematical truth, but we completely trick the computer into bypassing its physical limitations. It's brilliant. Now, seeing all these intricate math tricks, a very logical question pops up. If the math is really this incredibly fragile on our GPUs, why don't we just use hardware with more decimal precision? Like, why not just throw way more bits at the problem so we don't have to do all this crazy axis shifting in the first place?
Well, when we look at the actual silicon-level trade-off, the issue becomes pretty clear. Standard float32 has a massive max range. We're talking 10 to the 38th power, but it's incredibly memory-heavy. To train models faster, engineers really wanted to use 16-bit numbers. But look closely at standard float16. It allocates 10 bits to the mantissa, the decimals, and only 5 bits to the exponent. That means its maximum representable value is a measly 65,504. In a deep learning attention mechanism, dot products easily, routinely exceed $70,000. So if you try to train a transformer in pure float16, I guarantee you are going to hit a NaN crash almost immediately because it instantly overflows.
So here is the golden rule you need to remember. Dynamic range is vastly more important than decimal precision. Neural networks are actually incredibly resilient. They easily survive rounding errors. If a weight rounds from 0.141 to 0.14, the network barely even flinches. But if a value overflows and snaps to infinity, the network instantly dies. And this is the absolute genius behind Google's bfloat16 innovation. They willfully sacrificed decimal precision, dropping the mantissa all the way down to 7 bits, just to keep that massive 8-bit exponent range of float32. It perfectly aligns with how neural networks actually learn in reality. But look, even with the absolute best hardware, you can still fall into some nasty traps if you write custom code. Let me show you arguably the deadliest PyTorch trap out there. Imagine you manually code log of softmask. If your attention mask pushes a logit to -infinity, the softmask correctly evaluates to 0.0. But then you take the log of 0.0, which is -infinity. Finally, during backprop, the system tries to multiply 0.0 by -infinity. The IEEE 754 hardware standard forces this specific weird evaluation to equal NaN. Game over. But if you use PyTorch's fused kernel, f.log_softmask, it fundamentally restructures the math under the hood to resolve that limit to exactly 0, safely bypassing the trap entirely.
All right, to save you literally hours of troubleshooting headaches, here are my non-negotiable PyTorch pro tips. Number 1, as we just saw, never manually compute log of softmax. Just don't do it. Number 2, always use fused C++ kernels like f.cross_entropy. Breaking them apart to add your own custom Python logic destroys the bit-level stability they provide. Number 3, never manually scale mixed precision. You absolutely must rely on grad scalar's dynamic feedback loop so you don't permanently destroy weights on an overflow. 4, always use torch.log-Sum-Exp for dual-form contrastive learning losses, like when you're training CLIP. And finally, always clip your gradients and reinforcement learning to forcefully prevent weight explosion. To wrap things up, I want to leave you with this final mental model. Numerical stability is really just the art of shifting the fulcrum. Imagine trying to weigh an astronomically massive weight against a tiny, delicate feather on a standard scale. If you do it naively, the scale shatters into a million pieces. But by intelligently shifting the fulcrum, temporarily moving the mathematical balance point, you can weigh those values perfectly without breaking the physical hardware scale. The math remains identical, but you've mastered the machine. So the next time your model prints NaN, don't panic. Just ask yourself, where is the scale breaking and how can I shift the fulcrum? But it also makes you wonder, as our models grow to hundreds of billions or even trillions of parameters, what other unseen physical limits of silicon are silently shaping the AI architectures of tomorrow?